Now, as our functions become more complex when we're dealing with inequalities, it may be useful to switch rather than solving them algebraically, but solving them with a graph. Now, that's what we're going to do for this particular example and a couple of additional examples that involve absolute values, because again, they can become, especially when you have absolute values in combination with each other, or absolute values in combinations with squares, or absolute values in combinations with things that are not in absolute values, then it can just be somewhat easier to think about them as a graph rather than wondering about like what are all the options in terms of what the algebra can do. So let's consider the graph for this particular example, and I've plotted it in Desmos. And we can take a look at the graph. Along with the intersection, since we're interested in where the graph is going to be less than 0. And so we want to know where the graph is going to cross the y=0 line. Now, in this particular example, you can see that we have our two absolute values, and together even they produce also a V-shaped graph. But in this case, it's going to be opening downward because the 2x is going to basically dominate the x graph. It has a larger slope, so it's going to increase faster, and we're subtracting it. But it's not going to be even because in some cases we're going to be getting, in this case, a slope of -3, so it's going to be more steep when they're working together, and it's going to be more shallow when they're working against each other. And we can see that the 2 points of intersection are going to be -4. And in this case, the 0.66666, that is going to be equal to 2/3. So what we can say about our solution to this particular inequality, when is this graph going to be negative, less than 0? It's going to happen from -infinity to -4, not including -4 because it's not less than or equal to, and then union 2/3 to infinity. Now we can do something similar when we have a double inequality, 4 minus x less than 7. Now for this one, we need to be a little bit careful because we have inequalities on both sides. And so what we're going to do is we're going to plot 3 functions here. We're going to have to keep track of where the equal sign goes and where the not equal to sign goes. Now, if we go to Desmos and plot our 2 functions and then also mark all of the intersections, we get a graph that looks like this. So this is our line y=2, so that's the bottom end, and then the top end is the 7, and we want our absolute value to be in between these 2 segments. So that's going to be in this section right here, and also in this section right here. So in the x direction, that's going to be between -3 and 2, and then also from 6 to 11. Now, where it crosses the 2 is where we're going to put our square brackets. So since we're allowed to be equal to 2, but we're not allowed to be equal to 7. So this will be -3, comma 2 square bracket union 6, because that's also on the y=2 line, to 11. So notice my intervals are being reported in x values. The y values are just where the bounds are. What is our absolute value being bound by? Now let's look at another example. This one is also a double inequality, but it's a little bit more complicated because we have a square inside our function. Now, so let's go, we'll graph it similarly. We'll just change our upper bound and our inside function. Now, this problem is going to work somewhat similarly, although we're going to end up with non-integer solutions that we are going to have to find um, exact answers for algebraically. But let's look at the graph and see what our intervals are going to look like. So if I graph them, I get, so this blue line here is my absolute value. And you can see it looks very crazy. This is originally um, an upward facing parabola, but when it dips into the negative region, it flips up to become an upside down parabola. And then it's going to cross our lines 2 and 9 in a couple of different places. In one particular place, it's going to touch and then not pass through. So that's going to make our problems a little bit more complicated. So let's think about labeling these values so that we can refer to them more easily. So I am going to label this one A. Boy, it's trying to be helpful and it's not really helping. A. This is B. This is C. This is D. This is E. This is F. And this is G. Okay, so our 7 intersections. Now, we need to find exact values for these. These don't have obvious repeating decimals, although you can see we have positive and negative values of them on either side. So that will make it a little bit easier for us to find them, but we are going to have to find them algebraically. Now, the way that we can find them algebraically is we can take our absolute value apart a little bit. We can look at, well, just look at the endpoint of 2, this side, and then what happens if the absolute value does nothing? So what is that intersection? It's going to be when 2 is equal to x squared minus 9. And again, we're just looking for the intersections here because we can use the graph for when it's in between those ranges of values. We just need to know what those endpoints are. And then the other alternative is when the absolute value is applied and the inside of the absolute value is equal to -2. Now, the other end is going to do basically the same thing. We're going to be equal to 9 for our endpoints, and we'll come back and worry about whether they get included or not. X squared minus 9 equals 9, and then x squared minus 9 equals minus 9. Again, when the absolute value is not applied, so it's positive already, and then when the absolute value gets applied and it is something else. Now, if we solve each one of these equations, then we'll get our values for our intersections. If I move the 9 over, I get x squared is equal to 7, and so x is equal to plus and minus the square root of 7. In this case, if I add 9, actually this should be 11. Because it's 2 plus 9. And then here it's -2 plus 9, which is going to give me x squared is equal to 7. Jumping the gun a little bit. Plus and minus the square root of 7. So that's going to be these two inner values. And then on the top side, x squared is equal to 18. X is going to be equal to plus and minus the square root of 18, or plus and minus 3 square root of 2. And then in this case, this is going to be x equals 0, because we're going to get x squared is equal to 0. And so that's that one point that we have at the top. So let us write these down, which correspond which is which. So for for the top one, A and F, A is equal to negative 3 square root of 2, and F is equal to 3 square root of 2. G is equal to 0. That one we could actually tell from the graph. These other square roots, B is going to be negative square root of 11, and E is positive square root of 11. And then C is equal to negative square root of 7, and D is equal to positive square root of 7. Great, so now let's think about our original inequality. We wanted this absolute value, so that's our blue graph, to be in between 2 and 9. So that means this segment of the graph, and strictly in between 2 and 9, this segment of the graph, and then this segment of the graph. So in this segment, we're going from A to B. So our interval will be from negative 3 square root of 2 to our B value, negative square root of 11. Now, the one that gets the equality is where we cross the 2, which would be this B value. So that will become our square bracket. And then union, no comma, union. And then we're going to pick up at negative square root of 7, which will also be a square bracket. And then our graph is going to continue up to, but not including G. So comma 0, union 0, comma. So now back down to the square root of 7, square bracket, because that's on the 2 line, union square root of 11, comma 3 square root of 2, parentheses, because that's on the 9 line. So it's a very messy looking inequality, which is why solving it by hand can sometimes be a challenge. We can use the graph to assist us. However, if you choose to solve it by hand and you obtain all of these points, then you would follow the sign procedure. You would plug in values in between each of your endpoints and see whether it satisfied the inequality. For instance, is it between 2 and 9, for example? Now, one other example that we can do is when there is an absolute value and something that is not an absolute value that is included. So again, the idea behind the absolute value is that sometimes it applies and sometimes it doesn't apply. And so you could do this, again, solving it 2 different ways, and you would be solving 2 different quadratic inequalities. But we can shortcut the process a little bit by putting this on the graph. Now, if we plot this on Desmos, we get the following graph, and I've labeled the intersections. This is our x times the absolute value of x plus 5. That's this black curve. And our y equals negative 6 is going to be these values. And we want for this left side of expression with the absolute value to be greater than negative 6. So we want it to be in these 2 values, so in between here, and then also larger than this negative 2. So these are nice integer values, so we don't have to worry about like finding the exact square root values and everything else. We can just read this directly off the graph. Where is it greater? Again, um, in the x domain. So we're looking at the x values of our coordinate points. And this is a greater than or equal to, so we use the square bracket, -6, comma, -3, union, -2. And then, of course, we never use a square bracket on infinity.